Hello guys, this is Deepak RV and today we are going to have a brief session on understanding about the XGBoost algorithm. First of all, why we call it a scalable tree boosting system? That's because it is designed to efficiently handle very large data sets with millions or even billions of instances and features. This scalability is achieved through several key features and optimizations. The XGBoost is a versatile algorithm suitable for both classification and regression tasks. Slowly moving on. As you can see, these are the three optimization techniques in machine learning, especially in the gradient boosting frameworks like XGBoost. First, the sparsity aware algorithm. It efficiently handles missing or zero value data by learning default directions during tree construction. Next, weighted quantile sketch. It approximates optimal split points in weighted datasets for faster and more scalable tree learnings. Third, cache access, compression, and sharding. It's a system level optimization to speed up training by reducing memory overhead and parallelizing data processing. Now we are looking into the tree chart of XGBoost model. Here it is not a single tree like in the traditional decision tree. Instead, it's a collection of many decision trees built sequentially and iteratively. Each new tree in the sequence learns to correct the error made by the previous tree in the ensemble. This iterative process, guided by gradient boosting, results in a powerful and accurate predictive model. What all impacts had the algorithm created? It was used in 17 out of 29 winning solutions in the Kaggle ML competitions 2015, in which 8 solutions relied solely on XGBoost to train the model. It outperformed deep neural nets, which is the second most popular method in competitions. And other key applications are the sales predictions, CTR prediction, fraud detection, physics event classification, etc. Now, let's deep dive into the question, why XGBoost? It is designed to be fast and efficient even with larger datasets. It consistently outperforms other algorithms in various tests, providing accurate results. It can handle various data types including both numerical and categorical features and can also deal with missing values. The built-in regularization technique prevents overfitting, leading to most robust and reliable model. It provides feature importance scores, allowing users to understand which feature are most important in the model's predictions. Now let's take a look into the key optimization techniques and innovations in XGBoost. First, sparsity aware learning. It automatically handles missing zero values by learning the best default direction during the tree node splitting. Second, weighted quantile sketch. It approximates optimal split points on weighted data, enabling faster and more scalable distributed tree learning. Third, cache aware block structure. It optimizes memory access pattern for faster gradient statistics computation by storing data in compressed in-memory blocks. Fourth, regularized objective. It controls overfitting by penalizing complex models through rich L2 and lasso L1 regularization in the loss function. Regularized learning objective. As you can see, it's a technique used to prevent overfitting in machine learning models by adding a penalty term to the loss function. This penalty discourages complex models by shrinking large coefficients or encouraging sparsity, that is a situation where a large portion of data or model prevents parameters have a negligible impact. Here our aim is to minimize the regularized objective, which is combination of prediction losses and the regularization term. In the prediction loss, the convex loss function small l measures the difference between the predicted value and the target value. In the regularization term, it is further branched as leafy penalty and weight penalty. The leaf penalty term prevents overfitting and simplify the model. It adds a penalty term to the loss function that increases with the complexity of the leaf nodes. This discourages the model from creating overly complex structures. The weight term is to prevent overfitting by discouraging models from assigning excessively high weight to a specific feature, leading to more generalized and robust model. Gradient tree boosting. It actually relies on the intuition that best possible next model, when combined with previous model, minimizes the overall prediction error. The key idea is to set the target outcome for this next model in order to minimize the error. It optimizes an arbitrary differentiable loss function using gradient descent. First, let's look into the objective function. This formula defines the regularized loss function for the training a single tree at step t in XGBoost. It combines gradient statistics to approximate the loss reduction from adding the tree ft, while the regularization term omega of ft penalizes complexity. Next is the optimal leaf weight. Calculating optimal leaf weights is crucial for minimizing the loss function and improving the model's predictive accuracy. By finding the best weight for each leaf, the algorithm ensures that each leaf's prediction is so accurate as possible, contributing to the overall model's performance. Third is the tree structure score. This is to determine the best way to split data points within a decision tree, ultimately minimizing the overall prediction error. Higher the score, better is the tree. A greedy algorithm is a problem-solving approach that makes the best possible choice at each step, hoping to arrive at the optimal solution. An exact greedy algorithm is a specific type of greedy algorithm that is guaranteed to find the optimal solution to the problem. But exact greedy search becomes impossible when the data doesn't fit in the memory or in the distributed setting. So these are the three alternatives to the exact greedy algorithm in XGBoost. First, approximate algorithm. It accelerates split finding for large-scale data not in memory scenarios. Second, weighted quantile sketch. It enables the approximate algorithm to handle weighted data. Third, sparsity-aware split finding. It optimizes split evaluation for sparse data. Now we are looking at the three system-level optimization techniques in XGBoost design. First, column block for parallel learning. It pre-sorts data into columnar blocks, enabling parallel split finding across features and eliminating repetitive sorting ahead. Second, cache-aware access. It optimizes memory fetch pattern to minimize CPU cache misses, accelerating gradient statistics access by 2x. Third, blocks for out-of-core computation. It chops data into compressed disk-friendly block with background tree fetching, training on terabytes of data with desktop hardware. Here, you are able to see the comparison of major tree boosting systems. These 5 components form the end-to-end evaluation framework of XGBoost, systematically proving its real-world effectiveness across engineering, accuracy, and scalability. They collectively demonstrate how theoretical innovations translate into a production-ready system, from seamless implementation and superior performance to specialized task support and industrial-scale execution. This end-to-end evaluation bridges the gap between the algorithm design and practical deployment, cementing XGBoost as an internal solution for machine learning challenges. Before closing this presentation, I would like to conclude by saying XGBoost introduces sparsity-aware learning and weighted quantile for complex data, which, while its system optimizations like cache awareness, access, and disk sharding redefine scalable ML. These breakthroughs aren't just simply for boosting; they are blueprints for effective ML system. By merging algorithm innovation and hardware-aware design, XGBoost delivers industrial strength performance on real-world data, and the result, a framework that's as practical as it's powerful. And now finally, let's see how the algorithm works. As seen in the code, first the XGBoost library is being imported. Next, a dataset with 1000 samples or 2000 samples, 20 features and 2 classes is created. The test size 0.2 divides the data into 80% training and 20% testing sets. And finally, the code calculates the accuracy and precision values. The output displays high accuracy and precision, indicating the model is performing well on the test data. The classification reports break down performance of each class, showing balanced and strong results for both the classes. And all the obtained results prove that XGBoost is a robust and reliable algorithm for machine learning tasks involving structured data. Thank you.